This is SpaceTime, Series 25, Episode 10. Coming up on SpaceTime, intriguing carbon signatures discovered on Mars, stellar composition linked to how well they seed the universe with material for future generations, and a new study sheds light on the origins of life on Earth. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists have discovered an isotope of carbon on Mars, which on Earth is usually only associated with biological activities. The intriguing discovery, reported in the Journal of the Proceedings of the National Academy of Sciences, is based on the analysis of powdered rock samples collected from the surface of the red planet-scale crater by NASA's Mars Curiosity rover. Now, it's important to stress these findings do not necessarily point to evidence of ancient life on Mars. But they are fascinating. Scientists have not yet found conclusive evidence supporting the idea of current or ancient biology on Mars, such as sedimentary rock formations produced by ancient bacteria, or a diversity of complex organic molecules formed by life. Curiosity scientists are offering several hypotheses to try and explain the unusual carbon signals they've received. Their ideas are drawn partly from carbon signatures found on Earth. But the two planets, Earth and Mars, are so different they can't make conclusive definitive conclusions based simply on Earth samples. The biological explanation Curiosity scientists present in their paper is inspired by Earth life. It involves ancient bacteria on the Martian surface that would have produced a unique carbon signature as they released methane into the atmosphere, where ultraviolet light from the sun would have converted that gas into larger, more complex molecules. These new molecules would have rained down onto the surface and then could have been preserved with their unique carbon signature in Martian rocks. The Curiosity scientists also offered two hypotheses of non-biological explanations. One suggests the carbon signature could have resulted from the simple interaction of ultraviolet light with the carbon dioxide in the Martian atmosphere. Remember, there's a lot of it there. Something like 99% of the red planet's atmosphere is carbon dioxide. And that would have produced the new carbon-containing molecules, which would then have settled down onto the surface. The other idea simply speculates that this carbon isotope which they found could have been left behind from a rare event hundreds of millions of years ago, when our solar system passed through a giant molecular cloud which just happened to be rich in that type of carbon. All three hypotheses are possible. The six-wheeled car-sized Curiosity rover landed on the red planet in August 2012 and has been exploring Gale Crater ever since, taking samples and sending the results back to mission managers on Earth. Curiosity scientist Christopher House from Penn State, who led the carbon study, says all three explanations fit the data, and scientists simply need more data to rule them in or out. Now, to analyse the carbon in the Martian surface, House's team used a tunable laser spectrometer instrument aboard the Curiosity rover. It heated 24 samples from geologically diverse locations in Gale Crater to about 850 degrees Celsius in order to release the gases inside the samples and then measure the isotopes from some of the reduced carbon set free in the process. Now, isotopes are atoms of an element which all have the same number of protons in their nucleus, but different numbers of neutrons. And they're instrumental in understanding the chemical and biological evolution of planets. Carbon is especially important since it's found in all life on Earth, and it flows continuously through the air, ground and water in a cycle that's well understood thanks to isotope measurements. For instance, all life on Earth uses the smaller, lighter carbon-12 atom to metabolize food or for photosynthesis, rather than the heavier carbon-13 atom. Therefore, significantly more carbon-12 than carbon-13 in ancient rocks, along with other evidence, suggests to scientists that they are looking at signatures of life-related chemistry. Furthermore, looking at the ratio of these two carbon isotopes helps scientists tell what type of life they're looking at and the environment in which it lived. Now, on Mars, Curiosity researchers found that nearly half of all their samples had surprisingly large amounts of carbon-12, compared to what the scientists have measured in the Martian atmosphere and in meteorites. These samples came from 5 distinct locations in Gull Crater, which may be related as they all have well-preserved ancient surfaces. House says that on Earth, processes that would produce the carbon signatures being detected on Mars would have been biological in origin. The authors need to determine if the same explanation works on Mars, or if there are other explanations because Mars is so very different. Mars is unique because it may have started off with a different mix of carbon isotopes than Earth 4.6 billion years ago. The red planet's smaller, cooler, and has weaker gravity. As well as that, there are different gases in its atmosphere. Additionally, carbon on Mars could be recycling without any life involved. So, although scientists are finding things on Mars which are tantalizingly interesting, they still need more evidence to say they've identified life. After all, extraordinary claims require extraordinary proof. This is SpaceTime. Still to come. A new study shows that the composition of stars affects how well they see the universe and consequently future generations of stars. And a new study sheds light on the origins of life on Earth. All that and more still to come on SpaceTime. A new study shows that the composition of stars will affect how well they see the universe with material for future stellar generations. Stars are like giant factories. They produce most of the elements in the universe, including the elements for life. In that sense, we are all star stuff. But exactly what stars produce and pump out into the universe changes over cosmic timescales. 2 new papers published in the monthly notices of the Royal Astronomical Society and on the pre-press physics website archive.org have shed new light on how the youngest generations of stars will eventually stop contributing metals back into the universe. Now, astronomers refer to all elements as metals other than hydrogen and helium, the 2 primary elements produced in the Big Bang 13.82 billion years ago. That's not totally accurate because tiny trace amounts of lithium and beryllium were also synthesized. But basically, the universe started out as hydrogen and helium. So, the first stars to exist in the universe were formed almost exclusively out of this hydrogen and helium. And during their lifetimes and when they died, these first-generation stars, known as population 3 stars, fused together all the other elements on the periodic table. And those newly created elements were included in the composition of the next generation of stars to form. And as more and more stars were born, lived and died across the universe, more and more heavier elements or metals were produced in order to seed the universe and enrich subsequent stellar generations. But it turns out this ability to produce more metals changes depending on the composition of the star at its birth. And that's the essence of what these 2 studies are all about. One of the study's authors, Julia Chikravana from Monash University, says the introduction of just a tiny bit more metal into a star's makeup has really big implications on its evolution. Chikravana used modelling based on the other paper, that by her Monash colleague Amanda Karakis, to study the chemical output of metal-rich stars. Chikravana says they discover that at a certain threshold of the initial metal content of a star, it'll stop spreading more metals into the universe over time. Our Sun was born 4.6 billion years ago and is now a typical middle-aged star. It's what's considered to be metal-rich compared to the first generation of stars to have lived, and it has a heavy element content very similar to many other stars at the centre of the Milky Way galaxy. The new research predicts the evolution of stars formed more recently than the Sun and which have higher levels of metallicity, up to 7 times more metal-rich than our Sun. And the simulations show that really high levels of chemical enrichment cause these stars to act quite strangely compared to what the authors believe is happening within the Sun. Chikravana says the models of super metal-rich stars show that they still expand to become red giants and go on to end their lives as white dwarfs, just as our Sun will do in 7 billion years' time. But by that time, they're not expelling any heavy elements back into the universe. Instead, the metals are getting locked up in the white dwarf itself.
When we think about a star, it's a big ball of really hot gas, and that gas is made up of a few different elements. So in a star like our sun, that's around 73% hydrogen, 25% helium, and about 2% metals. So in astronomy, that's just everything on the periodic table that's not hydrogen and helium. So Amanda and I are looking at what happens if instead of 2% metals, we have 3 or 4 or up to 10% metals. How does that affect the star's evolution and its chemical contributions to the universe? So the first paper, led by Associate Professor Amanda Karakis, we were looking at the evolution of stars and how metallicity impacts that evolution. So there was a few specific processes we were looking at. And then the second paper, which I was lead author on, is looking specifically at how those processes impact the star's ability to contribute chemically to the universe.
So basically, 13.6 billion years ago, we started out with stars made purely of hydrogen and helium because there was nothing else. Maybe a sprinkling of lithium and beryllium, but basically hydrogen and helium. And these were very different in their physical characteristics and chemical makeup to the generations which followed them, because when those first stars ended their lives in spectacular supernova explosions, they filtered the universe, sprinkled the universe with processed elements, things that were produced either during the star's lifetime or in the explosion when it died. So as a result of that, the next generation of stars had a slightly different metallicity, a slightly different chemical composition. And when they died in turn, the same thing happened. They sprinkled the universe with chemicals that they produced, which may not have been produced by the first generations. And so as the universe has evolved, more and more of these metallicities, these heavier and heavier elements, are being sprinkled into the universe. And so the chemical composition of stars is changing. And we use our sun as a great benchmark because, well, it's the closest star we know and it's the one we can study best. And so we know what the sun's chemical composition is now. And what you guys have been doing is looking at how future generations will evolve from that and how that will further change, well, basically the way the universe looks.
Yeah, absolutely. So you're spot on. We would expect that if we have an example star, it would start off with, say, 1% metals in its gas. And then over its lifetime, we would expect that the chemicals that the elements that it's then spurting out into the universe is of a higher metal content than it started with. And what we're finding is that for our really metal-rich stars, the end product is the same metal content as it started with. So it's not contributing fresh metal.
So this evolutionary process has ceased in that regard.
At the very extreme end of the range, yes.
When you look at star factories, places like the Great Nebula in Orion and other places where stars are being produced, are you seeing that in molecular clouds?
So that's a good question. In terms of the Large Magellanic Cloud, for example, that's quite low metallicity. So when we look at the chemical kind of makeup of a galaxy, for instance, if we're looking at the Milky Way, in the past few decades, the sun has been kind of the limit for high metallicity. So that's been used as the metal-rich range, which means that when we talk about the really metal-rich regions of the galaxy, the bulge of the Milky Way, the sun is used as the extreme example. But we actually know that there are stars out there in the bulges of spiral galaxies which have much higher metal content than the sun. So we aim to provide a quantitative contributions from these higher metallicity stars, because then when we take that in the context of a galaxy, that can actually quite significantly change the chemical story of that galaxy.
Does that mean things like carbon stars may not exist in the future?
The reason why we see their contributions change so drastically is that if we're talking about how a massive star contributes chemically to the universe, it's quite intuitive. They undergo a supernova explosion. You can picture the gas being expelled from that situation. But for low and intermediate mass stars, which is what we studied in our papers, they contribute differently. So at the end of their lives, they blow up into these big, puffy, giant stars with really extended envelopes, and then those envelopes are eroded by stellar winds. So everything that's in their envelopes is contributed back to space. But we need, for thermonuclear reactions to occur, we need really, really high temperatures and densities that occur in the really dense core. So For the products of those reactions to be contributed back to space, we need a convective mixing process that kind of delves down into the dense core and mixes those products into the envelope where it can then be eroded by the winds. What we see in really high metallicity stars is that mixing process is eventually at a threshold completely stopped. So all of the elements that are being produced are locked inside that dense core that becomes the white dwarf, and they're not contributed into space. That also impacts their ability to turn into carbon stars, because for carbon stars to form, we need that mixing process to be able to scoop down into the dense region and pick up the products of helium burning, one of which is carbon, and move it into the envelope to change the composition of the envelope. So yes, at this higher metallicity range, we don't see carbon stars forming.
Do we see white dwarfs like that already, or is that something that future generations will only get to see?
Yeah, it's tricky to see this at the individual stellar level. It's more looking at particular regions of galaxies where we would expect these stars to have formed.
Are we seeing areas in galaxies where this process is already underway?
Yeah, absolutely. So we know that there are specific regions in particular galaxies where we find really metal-rich stars. So those are the bulges of spiral galaxies, such as our Milky Way, so right in the centre. And in giant elliptical galaxies, we also see very metal-rich regions where we could find these stars.
Where does your research take you now?
At the moment, so our two papers are based on low and intermediate mass stars. We're now moving up to the border between intermediate and massive stars. So that's about 8 to 10 times the mass of our sun, and looking at how metallicity impacts initial mass that is required for stars to explode as supernovae. So we had some results in the first evolution paper that suggested carbon burning was igniting at a lower initial mass than for lower metallicity stars in our really high metallicity models. And that's quite significant given that we're looking at a galaxy, it's heavily weighted towards low mass stars. So there are much more low mass than high mass. And that means that potentially if the initial mass for a supernova at a particular metallicity was lower than expected, that could lead to a lot more supernovae in that region of the galaxy. Our two papers are based on low and intermediate mass stars, which often don't get as much media attention as the exploding massive stars out there. But they're really important for a few reasons. One is that they dominate galaxies. So galaxies are full of low and intermediate mass stars. And the other is that we've got a big one in the centre of our solar system. So understanding how these stars evolve at different metallicities is really important and interesting for the sake of understanding our solar system.
That's Julia Chinkravana from Monash University in Melbourne. And this is SpaceTime. Still to come. A new study sheds light on the origins of life on Earth. And later in the science report, we look at the Tonga volcanic eruption, which is now being classified as the worst volcanic explosion in 30 years. All that and more still to come on SpaceTime. Scientists have discovered metal-binding protein core structures which appear to be common to all life on Earth, and which may have played a significant role in the origins of life in the first place. The findings, reported in the journal Science Advances, addresses one of the most profoundly unanswered questions in the universe. Exactly how did life first originate from what had been simple, non-living chemicals? In order to determine how life first formed on the planet, the authors first asked what properties define life as we know it. They concluded that for anything to be considered alive, it first needs to collect and use energy, either from the sun or hydrothermal vents. In molecular terms, it means the ability to shuffle electrons is paramount to life. Since the best material for electron transfer are metals, such as regular electrical wiring, and most biological activities are carried out by proteins, the authors decided to explore the combination of the two, that is, proteins that bind metals. So they compared all the existing protein structures they know that bind metals in order to establish any common features, based on the premise that these shared features would have been present in ancestral proteins and were then diversified and passed down to create the range of proteins we see today. Evolution of protein structures involves understanding how new folds arose from previously existing ones. So the authors designed a computational model that found that the vast majority of currently existing metal-binding proteins are somewhat similar, regardless of the type of metal they bind to, the organism they come from, or the functionality assigned to the protein as a whole. The study's lead author Jana Bromberg from Rutgers University, New Brunswick, says they found that the metal binding cores of existing proteins were indeed similar, even though the proteins themselves may not be. Bromberg, whose research focuses on deciphering the DNA blueprints of life's molecular machinery, says her team also saw that these metal-binding cores are often made up of repeated substructures, sort of like Lego blocks. And curiously, these same blocks were also found in other regions of the protein, not just the metal-binding cores, and in many other proteins that weren't even considered part of the study. Now, these observations suggest that rearrangements of these tiny little building blocks may have had a single or at least a small number of common ancestors, and they eventually gave rise to the whole range of proteins and their functions that are currently available, that is, to life as we know it. Now, Bromberg admits the science still has very little information about exactly how life arose from the primordial supervention Earth, but this work does contribute a previously unavailable explanation. Now, the discovery of this specific structural building block is also relevant for synthetic biology efforts, where scientists aim to construct specifically active proteins anew. And the findings would also be potentially useful in the search for life on other worlds. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. Scientists have determined that the volcanic eruption which rocked the tiny Pacific island nation of Tonga was the biggest volcanic eruption in the past 30 years. The massive blast generated 15-metre-high tsunamis and sent plumes of ash and smoke more than 20 kilometres into the air. Satellite images caught the huge explosion and shockwaves from space, and the sonic booms from the eruption could be clearly heard 2,300 kilometres away in New Zealand, therefore rivaling Krakatoa as the loudest noise ever heard by humans. Early estimates suggest the undersea eruption had a volcanic explosivity index, or VEI, of 5 or 6. And that is similar to both the 1883 Krakatoa eruption and the 1991 eruption of Mount Pinatubo. Like the Richter scale for measuring earthquakes, the VEI, or Volcanic Explosivity Index scale, is logarithmic, with a maximum reading of 8. Mount St. Helens was a 5. The tsunami waves generated by the eruption flooded wide areas of the low-lying Tongan island chain 40 kilometres away. The tiny kingdom of Tonga consists of 176 islands, and the effects of the eruption were devastating. Undersea communications cables were cut, many buildings are either missing or destroyed, and there have been multiple fatalities reported. Immediately after the initial blast, tsunami warnings were issued for nations around the Pacific Rim, with beaches evacuated in Sydney and all along the New South Wales coast. Boats were damaged by the tsunami surge in areas as widespread as New Zealand and California. Ash cloud from the eruption reached Australia 2 days after the blast, and scientists say pumice and volcanic ash are likely to persist for weeks, with further eruptions expected. So, what do we know about the actual volcano which caused all this mayhem? Well, it's roughly 1,800 metres high, approximately 20 kilometres wide, and it's been active for well over a century, with major eruptions in 2015, 2014, 2009, 1988, 1937 and 1912. The volcano breached the surface during the 2009 eruption, creating a new landmass between the islands of Hunga Tonga and Hunga Hape, which are remnants of the western and northern rim of the volcano's caldera, and are composed largely of basaltic andesite. Australian Air Force P-8 Poseidon surveillance and reconnaissance aircraft were the first on the scene, witnessing extensive damage and a thick layer of ash blanketing the islands. But actually getting to the people who need help was a bit more difficult. The runways were covered in ash, and that had to be cleared first. An Australian Air Force C-17 Globemaster was the first to land, followed shortly afterwards by a C-130 Hercules. These were carrying emergency supplies and equipment to the devastated region. Meanwhile, the Canberra-class helicopter amphibious naval assault ship, the Adelaide, has now also arrived, carrying several Chinook helicopters, a fully equipped hospital, water purification equipment, and humanitarian aid. New researchers confirm that people who've received a third COVID-19 booster shot do have much better protection against the virus compared to their double-vaccinated counterparts. A report in the journal Nature has looked at data on the effectiveness of the Pfizer and Moderna boosters compared to the double-vaccinated and those with no vaccination. For those who had AstraZeneca as their first two shots, researchers say the Pfizer booster is 89.6% effective relative to double vaccination at preventing symptomatic disease, while the Moderna was even better at 95.3% effectiveness. For those who had Pfizer first, the relative effectiveness of the Pfizer booster was 82.8% and Moderna 90.9% compared to double vaccination. And the effectiveness rates were always much higher compared to unvaccinated people. Meanwhile, Australia's Therapeutic Goods Administration has finally provisionally approved the Novavax protein-based COVID-19 vaccine. Subject to approval from the Australian Technical Advisory Group on Immunisation, ATAGI, the vaccine will be used as a primary vaccine for those 18 and older, but not yet as a booster or for children. Over 5.6 million people have now been killed by the COVID-19 coronavirus since it first spread out of Wuhan, China. However, the World Health Organization says the true death toll is likely to be at least double that amount, with almost 340 million confirmed cases. Now, an interesting side note to all this is a new study which shows that Australians are living longer because of the country's high COVID lockdown rate. State and territory governments impose strict lockdown conditions to keep COVID infection levels low. Melbourne had the longest lockdown period in the world. Now, researchers from the Australian National University have found the seemingly endless days of lockdown have actually increased life expectancy by an average of 0.7 years between 2019 and 2020. That compares to an average annual increase in longevity of 0.09 to 0.14 years, which was seen between 2015 and 2019. The findings, reported in the International Journal of Epidemiology, was the highest of all countries in the study. Denmark and Norway were the second highest, with both nations increasing longevity by 0.1 and 0.2 years for females and males respectively. Now, in contrast, the United States saw a decrease in life expectancy, with losses of 1.7 and 2.2 years for females and males respectively. Researchers say Australia's quick response to the COVID-19 pandemic, including closing borders and implementing strict lockdowns, is what differentiated Australia's longevity outcomes from that of the United States. It's been revealed that shortly after the 9/11 Al-Qaeda Islamic terrorist attacks, the British government under Tony Blair embraced a secret plan to use psychics to try and track down the terror group's leader, Osama bin Laden. The newly declassified documents show the UK Ministry of Defence even tried to recruit well-known internet psychics. Now, obviously, the psychics all failed. But it does show just how professionally national security was undertaken in Britain. And as Tim Mendham from Australian Skeptics points out, the British weren't alone. The United States CIA has a long history of testing psychics and those who claim to be capable of remote reading in the hope of getting an edge on the enemy.
The CIA and similar groups, if you read the book The Men Who Stared at Ghosts, will point out that the CIA and similar groups, the American military, try everything they can think of they come across just to see if there's
remote
something
sensing
there.
and things like this?
Yeah, remote sensing, all these things. They'll try anything just in case there's something there. There were suggestions that after 9/11 tried psychics to try and hunt down where he was. It's not surprising. It's probably seen that he'll try anything, and they did try everything, and not just psychics, but all sorts of things, that they did use this. So, yeah, it didn't work. It wasn't successful, like it never has been successful, these things that they tried out. But, yeah, they'll try it, and they have tried psychic powers before, well before 9/11, to try and sort of find missing people or baddies and that sort of stuff, and they've had similar results, as in zilch. But they'll probably keep trying. They're probably still doing it now, by all means. You never give up. The new generation of CIA agents and management will probably encourage them to try it again with the same results. So, yeah, they've been trying a whole range of things and they just, haven't worked.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.